Hello everyone, my name is Thomas Cook and I am a graduate student researcher at the University of Pittsburgh and a graduate student intern at the NASA Jet Propulsion Laboratory. My talk today is going to be on soft switching GaN-based isolated power conversion systems for small satellites with wide input voltage range. For some background on this project, future lunar and other space missions require power for both day and night operations operating in extreme high and low temperatures. Existing flight-qualified power converters using the flyback or forward topology are large, relatively inefficient, and expensive. The goal of this project was to develop a highly efficient, low-mass, high-density cascaded resonant power converter architecture in order to meet this need. The converter was designed to work with typical spacecraft bus voltages and provide a fixed 12-volt output, with the first prototype targeting 100 watts of output power. GaN devices are used primarily to enable the high switching frequency and high power conversion efficiency with their innate radiation hardness. The resonant topology chosen for this project is the LLC, which provides a wide zero voltage switching range on the primary FETs and zero current switching on the secondary FETs when operating at or above its resonant frequency. The transformer in the LLC can combine several passive elements into one component, such as the resonant inductor, the parallel path inductance, and the transformer itself, further reducing the component count and size of the entire converter, which aids to the high-density design. The frequency response of the LLC resonant tank is shown here, as well as its desired frequency operation range. By adjusting the switching frequency, the gain of the converter changes and allows for the converter to adjust its output voltage with respect to its input voltage. This, however, makes EMI filter design difficult. For this project, the resonant and switching frequency of the converter is selected to be at a fixed 1 MHz. This cascaded front-end converter will be used to adjust the bus voltage feeding the resonant tank to respond to any changes in input voltage or output voltage, such as during load transients. The buck topology was chosen as the input cascaded converter, which means lower voltage rated components can be used in the LLC stage. The buck converter provides a smooth input current for the LLC, and there is a variety of radiation hardened controllers available for the buck stage. Here is the full cascaded converter setup with the bus stage and the LLC stages shown together. The input buck converter is operating at 900 kHz and the LLC is operating at 1 MHz. All switches used are the GaN Systems GS61008T for topside cooled GaN FETs. The bus capacitance is 50 microfarads and the output capacitance is 100 microfarads, with the turns ratio on the transformer being 1:3 to allow for the bus voltage to change with respect to the output voltage to ensure consistent regulation. Here are some initial simulation results for the converter, with the output voltage ripple shown to be about 120 millivolts or 1% of nominal. The startup transient shows no overshoot due to the slow turn on of the bus voltage from the buck stage, and simulated average efficiency is between 90% and 95% for most of the primary load range. Thank you for listening to my talk. There is still a great deal of work to be done with this project, and we hope to have hardware results soon. Please feel free to reach out to me with any questions. Thank you.